Okay, so we have a question about why birds don't get electrocuted in power cables. Anybody have answer? Why the birds will not be electrocuted in power cables?
Not heavy enough.
No.
They are not heavy. Okay. How about if I touch the power lines? Will I be shocked like a bird or not?
Yeah, because you're on the ground.
Yeah, you said like depends on the ground. So if I was hanging on it, so it's not, will I be shocked? No. So what's the point is touching the ground, right? So the point is touching the ground, which is, in other words, the points to complete the circuits. Okay, what do I mean by completing the circuits? Because the current needs two things to flow, which is a voltage difference and a closed path. In power lines, definitely, of course, there is a voltage. But is there a closed path? Let's see. If you touch the ground, then there will be a closed path, so the current will flow toward your body, toward the ground. While if you still like hanging off on the cable, there is no closed path. Someone can say, okay, I'm claiming there is no closed path, but this is a closed path, right?
So we jump off a building and that.
Let's look at it. So let me imagine this is hand A, hand B, whatever, or point A, point B. Then the voltage difference between A and B is what? 0, right? So here I can imagine my body as a resistor. So whenever there is a resistor like this, what will happen? We call this what? Short circuits. This means this resistor will be neglected, so the current will flow only into the cable. And that's what's happening with the bird or with me when I touch the power lines. Okay? So the overall idea, there is no closed path for the current to flow, and there is no voltage difference. There is voltage, yes, on the power cables, power lines, but there is no voltage difference. So you need to have a voltage difference. While if you're touching the ground, then this will be something else. Like what? So here is point A with a resistor with my left hand, right hand, then here my body, then here is my left leg, right leg, then I'm connecting this to the ground. So I will say that this is point A, point B, C and D. So regarding to the node, C and D are the same node, while A and B are different nodes, right? This means this is positive, this is negative. So there is a voltage difference. Do you agree with me there is a voltage difference? Yes. Is there a closed path? Yes. So the currents will flow here, to the body, through your legs, then to the ground, then you'll be electrocuted. Okay? That's how.
What if you hung by one arm?
Yeah, even one arm, you can erase this. There's still closed path, right? You can remove this even if you're touching the ground by isolating yourself. Sometimes like safety shoes. Some safety shoes they can, for electrical, they can handle up to 1 kilovolts. So you will not be shocked even if you touch 1 kilovolts. This is for just the people who are, the technicians who are working on the power lines. So this depends on the thing, which is isolating yourself from the ground. Or in other words, we don't want to make a completed circuit. So even like, let's assume someone wearing a safety shoes. So you can work on live power lines, that's fine. But he cannot touch anything else. Like if for example, another person here, and for example, want to handle him, screwdriver or something else, so he cannot do it because they will be shocked together. Even he was isolated, but this one is not isolated. Whatever. The point is we don't want to be any closed path for the currents to flow, or no voltage difference as well. Now, some power lines are based on three-phase. What does three-phase mean? We will discuss this later, But most likely in power lines, when we have three-phase, we're going to assume there are 3 positive and 1 negative. We call it neutral. 3 lives, phase A, phase B, phase C, and 1 in neutral. So if the birds come only at single phase or for one of these phases, that's fine. There will be no problem. But if the bird, one leg at this phase, one leg at this phase, they will be shocked. Or one leg at positive, one leg at negative, they will be shocked. Most likely, when you have 3 phases, those phases are not equal to each other. So I would say A and B and C, they are not the same voltage. They are the same in magnitude, but different things. It's something we call a phase angle. Again, we will discuss this later. So there is a voltage difference between A and B, voltage difference between B and C, and the neutral. So whenever there is a birds or anybody touching 2 phases, even if there is no ground, then you will be shocked. So the thing that you will be safe if and only if you are only touching the power lines or the same line, not other lines. Okay? Just in the same wire. Don't go our same conductor. Don't touch one conductor on one hand, the other conductor on one hand. Then you will be shocked. Okay? And we see this also a lot in the for the birds and sometimes in power lines. We used to see a lot of bird remains. You'll see, like, for example, sometimes you'll see only the feet of the bird while the body goes out, like doing barbecue with it. So you will not, when we see for some instruments in the power line or in like transformers, whatever, you can see sometimes some bird remains. So this causes some problems or disconnection of the power lines. It happens once or maybe more than once, multiple times, because of the birds. And most likely this electrical power system, when there is a power off or outage off, they will be off for a few milliseconds, then it will try to reclose it, to restore the service automatically, to make sure is this temporary or something happening permanent. So if keep reclosing, then there's something wrong, then they will send a technician to fix the problem or detect where is the problem. So this, again, we see like a lot of birds on the power cables, and yes, they are safe, but this will not protect them from being shocked unless like if they are not touching any other power lines. Okay? So if there is no contact with any other things, then they are safe. Then the same thing like when any technicians working the power lines, if they are in the same phase or the same conductor, they can work even some situations that we do some maintenance under live networks, which is without disconnecting the power. When the power is on, we can do the maintenance. Okay, let's go to our topic, which is source transformation. In last lecture example, I mentioned that we did something called source transformation, and I told you that we will discuss this later. So what does source transformation mean? This means whenever there is a current source or voltage source with a resistor in series, they will be converted to be a current source and a resistor in parallel. So we can do it for any voltage source, but we need to have only a resistor in series. This is a must. And then we will convert this to current source and a resistor in parallel. And the vice versa as well. So V will be I, such that I is Ohm's law, Vs over Rs. R, or actually R is called R, whatever. R will remain as is, no change on it. How about the opposites? If I convert I to V, V will be Is times R. So there are some important things that you need to know when we do the source transformation. When we have, for example, this is Vs, and here is R. Can we do a source transformation for this one? The answer is no, because we have a parallel resistor, so no. How about when we have this current source with a series resistance? Can we do a source transformation? No, because it's current source. And the current source it must be in parallel, not series. The resistor must be in parallel. So keep in mind, the source transformation is not only applied on the voltage source or current source, it's applied on both voltage source with resistor in series or current source with a resistor in parallel. So voltage source with R in series, this is a must with R in series, to be current source with R in parallel. Okay? Again, it must be in parallel, otherwise I cannot do my source transformation. Then the formula, which is I times R, which is Ohm's law, or V over R. Now, also you need to look at the voltage polarities. Let me give you some scenarios. So when I have plus minus V source, R source, this can be converted to be current source and a resistor. Keep in mind, look at the voltage polarity and the current direction. So when is the voltage polarity like this, the current source will be up. If the voltage polarity like this, like the positive at the bottom, then the current source direction will be like this way. So you need to keep this in mind. The positive of the polarity must be at the top of the arrow. So let's assume the other scenario, which is when we have like the negative. And here is our source. So when I do a source transformation, the arrow will be down. Then here is the resistor. Okay? How about if I assume like this? What will happen for the transformation? Here is V source, here is R. It will be like, here is the current source, here is a resistor. So you see like the arrow at the positive side. And now the last thing, which is whenever we have this kind of source, this type of sources, then it will be the arrow, the top of the arrow will be at the positive side. So it's also very important, not only when you convert this, just convert it, look at the polarities and the directions, voltage polarity or the current direction. Okay? So these 4 scenarios can explain the situation. Is this clear? Again, whenever we have voltage source with a series, with a parallel resistor, this is, of course, does not mean current source with a series resistor. This is definitely wrong. Okay? You cannot do a source transformation with a series resistor with current source or parallel resistor with voltage source. You cannot do it. They must be like this. Any question? Now, when you look at this, this circuit looks familiar with us. Is this correct? I think we've seen this before. Anybody knows where? Do you know where did you find this? Voltage source with a series resistor, current source with a parallel resistor? Where? We've seen this before. Nortons and Thevenins, right? So let me just show you something here about Nortons and Thevenins. So we realize Nortons and Thevenins are actually source transformation of each other. Right? So that's also another way. When you do Nortons, find Thevenins first, then do the source transformation, then you find Nortons. And that's what we actually were doing. So I will be V over R, and R will be the same, which will be parallel. Okay? So Thevenins and Nortons are examples of source transformation. Now let's go to another thing, which is voltage sources and series resistors equivalents. When we have, all of them must be in series. If they are not in series, we can't do it. We cannot do the simplification if they are not in series. If they are in series, the resistors can be in series. So the equivalent resistance will be 8 plus 4 plus 1, which is 13 ohms, right? Now, how about the sources? We realize that if we have series voltage sources, we can combine them together. And we can do actually series sources, not only series resistors. But the thing which is, we cannot say, let's add them together or subtract them together. We need to assume a polarity, then we might be either adding or subtracting. Like what? In this example, we need to assume them or convert them to be a voltage source with a resistor. So the voltage source, or the resistor actually, because it's easier, 8 ohms, 1 ohms, and 4. So 8 plus 1 plus 4, which is 13 ohms. Now with the voltage polarity, the first thing is you need to assume a voltage polarity. So let's assume a voltage polarity like the positive at the top, the negative at the bottom. Then here, look, like try to go counterclockwise, or clockwise actually, and see which one is the same as my polarity, which one is the opposite. 2 volts, is it the same or the opposite of my reference?
Opposite.
It's the opposite, so it will be -2. 12, is it the same or the opposite? The same. So plus 12. How about 5?
Plus 5.
Opposite, right? -5. How about 8?
Same.
The same. Plus 8. -2 plus 12, 10 minus 5. 5 plus 8, 13. So it will be 13 volts. Okay? So you need to assume your own reference. How about if, let's assume someone else say, I'm going to assume the opposite direction of the opposite polarity. Will this be okay? Yes, it can be okay. But you need to be consistent when you do the simplification. So for the resistance, will be 8 plus 1 plus 4, which is 13 ohms, no problem with this. Now for the sources, let's look at the 2 volts. It's the same as my reference, so it's +2. 12, opposite, -12. 5, it's the same, +5. 8, opposite, -8, so the answer will be -13 volts. So you can see that here in the top we get 13, the bottom get -13. And we say the -13 means the real life direction is the opposite way. Then both of them are the same answer. Okay? Remember, according to vectors, whenever you see a negative sign, this means it should be the opposite thing. So with regard to the voltage, means the real life voltage is the opposite polarity of what we have here. So when we have -13 volts, this means the real life polarity is the positive must be at the top, then it will be 13 volts, which is consistent with the top circuit. Okay? Again, this happens if and only if we have series sources, series resistors. If we have parallel, we cannot do it. So, I said series, not series. Now, if we have this example, like 5 volts, 6 ohms, 2 ohms, plus minus 2 volts, then whatever, 5 ohms, 10 volts, we cannot do this simplification because we have some elements parallel, some elements different, that they are not in series. So there is no way to do the simplification. While if I add, for example, plus minus 5 volts, I can only add these two, which they will be as plus minus 10 plus 5, which is 15 volts. Okay? So remember, when you do the series sources, you can do it only if and only if they are in series. The second thing, which is look at the voltage polarities and the current directions. They are not like the resistor. The resistor series, just add them. While for the sources, some of them you need to add, some of them you need to subtract, depending on your reference voltage polarity. Then the same thing for the current sources. We can do it for the, when we do it for the voltage sources, we can do the current sources. But the current sources, keep in mind, they must be in parallel. You cannot do that if they are not in parallel. So let's look at this circuit and we need to do the simplification. So let's assume my reference is, we need to convert the circuit to be this one. So we have 12 and 8, which is 12 parallel with 8. Then we will do the parallel things. So I think the answer will be 12 times 8 over 12 plus 8, which is 4 ohms. Now regarding the currents, I'm going to assume that the arrow or the top will be up. Then look at the current sources. So we have 9 amperes, the first one. Is it the same as my direction? Yes, the same as my reference, so plus 9. How about 2? The opposites, minus 2. How about 5? The same, plus 5. So the answer will be 12 amperes. Okay? Does this make sense? How about if I say, like, someone assume the current arrow goes down? Will this work? Yeah, it will work. And let's find the value. So here it's 4 ohms. Then make the arrow down. So let's try with this one. So here 9 is the opposite, so it will be negative 9. 2 is the same, plus 2. 5 is the opposites, so minus 5. So the answer will be negative 12 amperes. So the negative sign of the current means the real current direction is the opposite way of my assumption, which is consistent with the top circuit. Then both of them are correct. Is this clear? So we now realize whenever we have multiple sources, we can combine them if and only if we have series voltage sources or parallel current sources. Otherwise, we cannot do it. Let's assume this scenario. We have a current source like 9 amperes, 2 ohms, 3 amperes. Now I have the question, which is, can I combine 3 amperes with 9 amperes? They look like parallel, right? Can I combine them? The answer is no. Why? Because this resistor creates a problem. They must be pure parallel, actually. They are not in parallel. The branch is in parallel, or the essential branch is in parallel, not the 3 ohms. So you can prove this by labeling the nodes. This is node 1, this is node 2, this is node 3. So 9 amperes between 1 and 2, 3 amperes between 2 and 3. Then they are not in parallel, right? Then we cannot do the simplification. So no simplification. Okay? So you need to be careful. You need to be careful. Whenever you do combine any voltage sources or current sources, there must be pure series or pure parallel. Okay? Now let's look at this example. Use source transformation to determine the current and the power in the 8 ohms resistor. So most likely here in this example, I'm going to force you using source transformation. But later in the quizzes or the exams, you will not be forced. So I'm telling you, find the currents that's at the 8 ohms resistor, or the power, whatever, the current and the power. And I will not mention anything. So the good thing about source transformation, you will use it if you need it. Sometimes you can use other techniques, and you don't need to use source transformation. You can do KVL, KCL, Ohm's law, and that can be fine. So source transformation is like a tool that you will use it if you need it. So you have a toolbox. You don't need to use everything, right? Use whatever you need. Then I'm just here, like for the source transformation, even series voltage sources, parallel current sources, all of them, put them in your toolbox and need them if you use it, or use them if you need them. Okay? This does not necessarily I'm going to use them. But here in this example, I want to show you a demonstration how we do source transformation and how this will make the problem easier. Sometimes you can solve this problem without source transformation, but this might take long. Maybe it takes 15, 20 minutes to solve this problem, while when you do source transformation, it can take 5 minutes. So sometimes it can be shorter, make the life easier. But without it, we can still live, but it will take more time. So the situation is we need to determine the current here at the 8 ohms resistor. How to find the currents? We need to apply source transformation. So where can we apply source transformation? So we will say that, let's look at 3 ohms and 5 ohms. Can we do a source transformation here? Yes. Why? Voltage source, resistor in series. Since they are in series, then yes, I can do it. So this will be converted to be a current source, and the top of the arrow will be up because the positive is up. And here the 3 ohms resistor remains, no change. Now what's the value of the current source? Will be V over R, which is 15 over 3, then it will be 5 amperes. So what we will do later? Redraw the circuits. Make sure to redraw the circuit and see what we will do. So we just redraw the circuit like this way after we did the source transformation. Now, what else? It's still, actually, it makes the problem more complicated. So how can I solve the circuits? Using source transformation. Now, can I do source transformation here? Yes, I can. Okay, but when I do it, what's the benefits? I will go back to the origin, right? Yes? Yes. So there is no point of doing source transformation like this way. My target is try to make it as a single loop. How about if we try to make it simpler, like 6 ohms and 3 ohms, making them in parallel. So we will have only a single resistor. Then when we do the source transformation, it will be as simpler actually. So 6 and 3, they are in parallel. So the equivalent will be 2 ohms. 6 times 3 over 6 plus 3 will be 2 ohms. So the equivalent circuit here is, I can redraw it to be like 3 amperes, 10 ohms, 8 ohms, 2 ohms, 5 amperes. Now, I need to find the current using source transformation for the 8 ohms. What should I do? Using source transformation. What do you think? Is there any sources here? Yes, we have current sources, 3 amperes and 5 amperes. Can I apply source transformation for them? Yes, I can. Current source with a parallel resistor, then this means yes, I can. We can do source transformation here and we can do it here. So basically, this will be as plus minus, and here 10 ohms remains for that portion. So it will be 3 times 10, which will be 30 volts. Then 8 ohms remains. Here we have 2 ohms. Then the source, the positive at the top, like this way. And it will be 5 times 2, which is 10 volts. Okay? So basically we did, this is the first portion for source transformation, this is the second portion. Okay, does this make sense? Now, how can I find the currents? You can look at this circuit and do some simplification. So all of this are series, right? Or all of this are in series. So we can do 30 volts and 10 volts are in series. Then we can do simplification. So whenever we do the simplification, this is my reference voltage. So 30 minus 10, because 10, when you go counterclockwise, when you go clockwise, it will be the opposites. Then we have 10 plus 8 plus 2, which will be 20 ohms. So this will be 20 volts, 20 ohms. Then we can find the current easy, which is I will be voltage, the sum of the resistors. So the voltage is 20 over the sum of the resistors, 20, then it will be 1 amperes. Now we just calculated the current, which is 1 amperes. The second thing, to calculate the power at the 8 ohms resistor, I square times R 8 ohms resistor. So which will be 1 square times 8, the answer will be 8 watts. Okay? Now you need to know how to do the circuits in much faster way other than like spending a lot of time and over-explaining these situations. So try to make it as fast as you can. This is one approach that I did. There is another approach written here by doing KVL without simplification of voltage sources. So whatever more convenient for you, you can do it. We can do KVL to find the current, then apply I squared times R. So you can see sometimes there are multiple ways to solve the circuit. All of them can be correct. That's fine. Any question? Okay. Let me pause a little bit, then we will go to the next example in source transformation. Yes, I'm sorry. 8 ohms because we need to find the power at the 8 ohms resistor. That's the question. Yes.
Why is I squared?
It is the power I squared times R.
Say it for me.
It is V times I, or you can I squared times R, or V squared over R. That's it. Any other question? Okay, let's go to the next example. Use source transformation to find I/O. I/O here, which is associated with the 4 ohms. Now we need to do source transformation. Can we do source transformation here, 4 and 20? Yes, we can. But actually here it will be, why we need to do it? Because the question says find I/O here. So if I do a source transformation, I/O will disappear. So there is no reason to do source transformation for this portion, right? Because I/O will disappear. My target is to find I/O. I/O, again, is the current flowing into this branch. This is I/O. So whenever it says like this, I'm not going to play with this. So let's leave it this part as is. Then let's look at the other things. My target is try to make it as single loop, so the problem will be easier. How can I make it as a single loop? By looking at the other sources. Any thoughts? How can I make it as a single loop?
Source conversion to current sources.
Two current sources. Now, can I do voltage source transformation? Yes, because current source, resistor in parallel. Correct. So here and here. Then this one, it will be as the positive at the top of the arrow. Then here is the resistor, 5 ohms. And this one will be 3 times 5, so which will make it 15 volts. Then here, it will be as the positive at the top of the arrow. Here, 2 ohms remains. Then this will be 6 times 2, which is 12 volts. Then redraw the circuit with the new modification, which is end up having this 12 volts, 2 ohms, 15 volts, 5 ohms. So how can I solve this circuits? You can either find the equivalent series sources, or you can do KVL. Here in this example, I did KVL, or let me do it now with the other way. You can look at the KVL later, which is substituting first, like doing the voltages, then do Ohm's law for all of the resistors. So then you can do it. Or we can make it as, I'm going to assume my reference voltage like this way. Then here is the reference resistor. So the resistors, we have 2, 5, 4, which is all of them are in series. So the answer will be 11 ohms. With the sources, my reference is like this way. So I'm going to assume here is 12 volts, or actually plus 12, because 12 volts is the same as my direction. 15 volts is the same, so it will be plus 15, while 20 volts is the opposite, minus 20. So the answer will be 7 volts. Now we need to find I/O. So I/O will be V over the sum of the resistors, which is we have 7 over 11, which is in other words 0.6364 amperes, or in terms of milliamperes, 636.4 milliamperes. That's one way, or the other way using KVL. The other way KVL. So whatever you want, you can do. Whatever you think more convenient for you, you can do. You have these tools, you have these tools. Use the easiest tool for you. Okay, again, solving the circuit analysis is not unique. You can have multiple ways. Your job or your target is to look for the easier way. What's the easiest one? Use the easiest one, then try to make it in shorter time, less calculation to avoid a lot of mistakes, avoid some unnecessary simplifications, like in the beginning of this example I said we can make 4 and 20 we can do source transformation. Yes, you can do, but it will be useless. So sometimes avoid like this kind of useless simplification, this kind of simplification that creates some problems. So sometimes you can do source transformation, but it will worsen the problem. Okay? Now, let's go to another tool as well. So again, by the way, today's lecture, all of them are tools, which is use them if you need them. So even without today's lecture, you can pass the course. Even if someone say, I don't want to study today's lecture, you still can pass the course, that's fine. But again, some problems can take longer time, sometimes shorter time. So our target now is not only to solve this DC circuit, it's to solve it in shorter time and optimize your time, optimize your work. Voltage division. What does voltage division mean? When we look at this problem, how we can solve it, we need to find V1, V2, V3. We used to say in the past as it is single loop, then we did calculating the currents. I equal the voltage source over the sum of the resistors, right? Then we used to say V1 will be I times R1, which is going to be V source times R1 over the sum of the resistors, right? That's what we used to do. Oh, let me write one. Then we used to find the current first, then find the voltage. That was for voltage division. I'm sorry, that was what we used to do before. Now, in voltage division, we said you don't need to calculate the currents. You can skip one step. You can calculate the voltages in faster time without the need to calculate the currents. How? Look at this example. We need to calculate V1. V1 will be the resistor R1 times V source over the sum of the resistors. How about V2? V2 will be R2 times V source over the sum of R2 of the resistors. V3 equals to R3 times V source over the sum of R3. We realize this term is constant for everyone, right? Or this term is constant. The only thing that's changing is we said V1 R1, V2 R2, V3 R3. That's it. Use the corresponding resistor. So when you're calculating V1, V1 associated with R1, V2 associated with R2, V3 associated with R3. That's it. So we don't need to calculate the currents. This makes the problem easier, so we can find the voltages in easy way. Even you can find it in your head without doing any calculation. So as a summary, we will say V for element I equals R for element I times V source over the sum of the resistors. Keep in mind this is applied if and only if we are in series. Are in series. Okay? For example, let's assume this circuit. Here is V source, here is R1, here is R2, here is R3. So this is V1, this is V2, this is V3. Now, can I do voltage division here? No, I can't. Why? Because we have R2, R3, not all of this circuit, it's not single loop, we will say. How can I do voltage division if I do like with this circuit? You can simplify this circuit by doing parallel of R2 and R3. Here is V source. Here is R1. Here is R2 parallel with R3. So this is plus minus V1. Here is plus minus V2, which is equal to V3 because in parallel. Now you can do the voltage division if they are single loop. Okay? Let's have a look at this example. Exercise. Determine the voltage between A, B, C, D. So I'm going to call this as V1, V2, V3. How can I calculate them? So basically, we will say that V1 equal V source equal to, sometimes we write it like V source times R1 over R1 plus R2 plus R3, which is going to be as V source, we have 25 times R1, 1 kilo over 1 kilo plus 8.2 kilo plus 3.3 kilo. Kilo will cancel each other. Then V2 equal V source over R2 divided by R1 plus R2 plus R3, which is 25 times R2, 8.2 over 1 plus 8.2 plus 3.3. Then V3 equals V source times R3 over R1 plus R2 plus R3, which is going to be as 25 times 3.3 over 1 plus 8.2 plus 3.3. Actually, I don't have the answers, but you can calculate them using the calculator to find the overall answers. Okay? Any question? Now here in this topic, I mentioned voltage division. Is there something called current division? Yes. We have current division. Voltage division, we do it in series. Current division, we will do it in parallel. Because current and voltage are the opposite of each other. Current division, we can do it if we have parallel. So basically, current division, we will do a special case here. Special case. For only two currents. Or two branches, two connections. Which is, let's assume this circuit. No matter what we have here, voltage source, current source, whatever, our target is just to observe these points. By observing these points, we have I here, this is I source, we have I1, I2. How can I calculate I1? How can I calculate I2? What we used to do before, which is we used to calculate the voltage, try to calculate the voltage, like doing simplification, like do these two in series or parallel, then find the equivalent resistance, we will find the source currents, then find the voltages, do KVL, then we will do Ohm's law for R1, to find I1, Ohm's law to find I2, something like that. But now we can skip all of this. If we know the source currents, we can calculate I1 and I2 easy. Basically, I can say that I1 equals to I source over the sum of the resistors, R1 plus R2. But here we will use R2. Then, whenever we do I2, equal I source times R1 over R1 plus R2. So what you can notice, for 1, we use 2. For 2, we will use 1. Okay? We will use the neighbor resistor, not the resistor itself. Look, here I1 is I2 associated with R2. I1 is associated with R1. But when we do the current division, use the others, use the neighbor resistor. Okay? This is different than voltage source. In voltage source, we used to use the corresponding value or the same value or the value associated, the resistor associated with V1, we will use R1, V2, R2. Now, for I1, for the current division, we will use the opposites. I1, we will use R2. I2, we will use R1. Okay? Just use the opposite. Use the neighbor resistor. So please be careful, because I used to see many mistakes before, which is many students, when they do the current division, they put the formula fine, but they are using the corresponding resistor, which is assuming similar to voltage division. And it is not. This is fatal mistake. Okay? Example about the current division. Actually, current division should be applied for only 3 resistors, so I'm going to erase this one. Just eliminate. for 2 resistors or 2 elements. We will not discuss. It can be applied for 3, but there is different formula, and it's out of our scope. So let's assume this is R1, this is R2, and we have here the source current. This is I source. It will be split to be I1, here is I2. Then we will say that I1 equals to I source times R2 over R1 plus R2, which is I source here 10 milliamperes, times R2, which is 220 over 330 plus 220. Then to find I1, and the answer I think it will be about 4 milliamperes. I1 will be I source times R1 over R1 plus R2, which is going to make it 10 milli times 330 over 330 plus 220. So the answer will be 6 milliamperes. So keep in mind when we calculate for I1, I2, this is actually, let's fix it. When we calculated for I1, we used R2. When we calculated for I2, we used R1. This is just the thing that need you to be careful. Okay, any question? Now I'm going to write some textbook problems for current division, voltage division. These are important. This is actually from chapter 2, 2.13, 2.14, 2.17, 2.21. Now we are done with chapter 1 and chapter 2 and chapter 3, and we are done with the DC circuit. Starting from next lecture on Monday, we will start discussing a new topic, chapter 4, which is transient mode, something different than DC circuits. So see you in Monday. Have a great weekend.